Hello, and welcome to this discussion on the various types of heat exchangers. Now, heat exchangers are typically classified by their arrangement and how they're built. By arrangement, we mean the type of flow. So we can have a parallel flow example, like the figure A here, where the two fluids are flowing in the same direction. Or we could have a counterflow design, where the two fluids are flowing opposite directions, as we can see in figure B. We also have cross-flow heat exchangers, where the fluids are flowing perpendicular to each other rather than parallel. Now, the simplest version of a heat exchanger is what we call a concentric pipe. It's one pipe within another pipe, and the fluids flow in the central pipe and in the region between the two. Now, we also want to note here that in a heat exchanger, all the heat from one fluid must move into the other fluid. This is convenient because we can use the first law in each fluid. Now, the first law says that total heat flow has to be equal to mass flow specific heat times delta temperature. So what we can do for a heat exchanger is say that the total heat transfer has to be the same for both cases. So what that means is mass flow times Cp times temperature change for fluid 1 must be equal to mass flow times Cp times temperature change for fluid 2. So we can set those two things equal to each other. Now, this is just from thermodynamics, but later on we're going to look at heat transfer to help us figure out exactly what that temperature difference is going to be. Now, for the parallel flow design, the maximum possible heat transfer occurs when the length is infinite. And at that point, the exit temperature is going to be equal to the average temperature of the two fluids. It's going to be a mass-weighted average temperature. For a counterflow design, on the other hand, the most possible heat transfer, this again occurs when the length is infinite, but at this point, one fluid is going to have reached the inlet temperature of the other fluid. So a counterflow heat exchanger has the potential to have higher heat transfer than a parallel flow heat exchanger. This is the reason that the infinite counterflow heat exchanger is used as sort of the ideal heat exchanger, the maximum possible performance. And then we use effectiveness to compare the real heat exchangers to this ideal case. And we're going to define effectiveness later, but it comes into play when we're looking at analyzing and designing heat exchangers. Now, there are going to be many variations on this design. We're going to talk about a few of them. Mostly, we're looking at what are called recuperators. Recuperators are what we'll be discussing mostly for this class. They're the most widely used type of heat exchanger, where the fluids are separated by a wall, and then we have to have heat transfer through the wall to move the heat. But you can also use regenerators, where the hot and cold fluids are alternately pumped into a chamber that's full of something that stores heat. So they might pump hot fluid into a chamber full of metal spheres that then heat up. And then they remove that fluid and put a cold fluid into that same chamber to absorb the heat from the metal spheres. And there's also direct contact heat exchangers, like droplet cooling or spray cooling. In some cooling towers for power systems, they actually spray the liquid directly into the cooling tower, so it comes into direct contact with air and transfers heat that way. Now, one of the most common types of recuperators or heat exchangers is the shell and tube design. It's actually the most common in industry. They don't usually have the highest effectiveness or efficiency, but they are very cheap to build and easy to maintain. Think something like steam generators in pressurized water reactors, liquid metal fast breeder reactors, high temperature gas reactors, and so on are all going to be variations on this design. Sometimes they include baffles, as you can see in the figure, and that just helps to mix the fluid and improve the total heat transfer. If you need to have additional performance, you can actually attach these heat exchangers in series to one another, so you have multiple shell and tube heat exchangers. But the problem here is that each additional shell has essentially a reduced return on investment. So if you're looking at this, you need to balance the construction cost and maintenance cost against the improved performance for the heat exchanger. Now, you can actually use fins on one of these heat exchangers for like a cross-flow shell and tube heat exchanger, as you can see in the upper left figure. The fins are going to help improve heat transfer, especially when the shell side is a gas. And the reason is, for gases, heat transfer coefficient tends to be very low. So increasing the total area that the gas is flowing over tends to help reduce the convection resistance for the problem and improve the heat transfer. Microchannel heat exchangers have also become very popular recently for many applications. The flow channels here are very small, So you end up with a very high surface area to volume ratio, which is very good for heat transfer. And these may include things like printed circuit heat exchangers, where you have a metal plate and you use machining to carve out tiny flow channels. You may have brazed plate heat exchangers, where you put plates with flow channels machined into the surfaces together, and you push them together under high temperature and high pressure, so they basically weld the plates together. There's many other types. The drawback to these is that you have a very large friction loss or head loss for the fluid as it flows through the heat exchanger. So this requires additional pumping power, which again is going to be more expensive than traditional heat exchangers for operation. They're also much more sensitive to fouling by corrosion and dirt and blockage of heat exchanger channels because the channels are so much smaller. The reality is there's almost as many heat exchanger designs as there are designers. So it's going to be impractical to cover every possible case in this class. But most heat exchangers are going to fall into a few broad categories: parallel flow, counterflow, cross flow, shell and tube, concentric tube, printed circuit, etc. So we'll be doing some problems and analysis on some of these general types of heat exchangers. And then later on, you'll be able to take these lessons to more specific versions.